Hi everybody, this is Mr. Kearns going over the weeks 5 and 6 remote learning packet for Global, Math, Forensics, and ELA. The teachers involved are Mr. Ian Diorio, Mr. Colvin, Miss Kelm, Mr. Kearns, and Miss Cindy for Forensics. All right, the theme that ties the packet together for these 2 weeks is the scientific revolution changed the perspective of scientists and medieval scholars forever. First course is Global Studies, and the objectives are to understand the characteristics of World War II warfare and explain the effects of these characteristics on those involved. We're going to describe what the scientific revolution was, and we're going to compare the medieval view of the world and the truth with scholars in the scientific revolution. Directions. List 2 things that you know about the natural world. Then identify how you know these things are true. What was the scientific revolution is the essential question. So the example here is something I know. Fire is hot. How do I know it? I know this because I once burned my hand on the stove fire and it was very hot. So you're going to write something else you know about the natural world, and then you're going to explain how you know it's true here. And the same thing for the second example. The scientific revolution, you're going to watch the video from start to minute 2 and 29 seconds, and then read the text below and answer the questions that follow, okay? The link is here. You can also click here, and it'll open up the YouTube video. The scientific revolution was a period of time from the 1500s through the 1700s in which scholars started to question their beliefs about the world and base their conclusions on observation and reason rather than spiritual belief or what organizations like the Catholic Church told them. Scholars who studied the natural world were often called natural philosophers during the scientific revolution. The term scientist was not used until the mid-1800s. Scholars questioned whether the Earth or Sun was at the center of the solar system, why things fall down instead of up, how the human body works, and many other topics in astronomy, anatomy, mathematics, biology, chemistry, and physics. To guide them in their discoveries, scholars followed a new process called the scientific method, which emphasized the importance of experimentation, observation, evidence, and working with other scientists to confirm their results. The rebirth of the European economy, the start of more universities around the continent where researchers could work, and the use of the printing press to circulate new ideas created a community of scholars who built on one another's achievements to gain a better understanding of the world and push innovation forward. Like the artists in the Renaissance, scholars during the scientific revolution owed the foundation of their work to Greek, Roman, and Muslim scholars that came before them. Trade between the Ottoman Empire and Europe and Byzantine scholars who left Constantinople for Italy after the Ottoman Empire conquered it in 1453 led to the rediscovery of Greek and Roman texts that had been kept in the Middle East during the chaotic European Middle Ages. In addition, Muslim scholars made great strides in science, and their ideas were shared with Europeans and contributed to the discoveries made during the scientific revolution. The scientific revolution changed the way that people look at the world and how one finds truth, and provided later scientists with the tools they needed to make advances in technology that shaped the rest of global history. So, question 2, what was the scientific revolution? 3, what changes resulted from the scientific revolution? 4, what topics did scholars investigate during the scientific revolution? 5, where did the ideas that influenced the scientific revolution come from? And 6, define the following terms: scientific revolution and scientific method. Page 4 begins, how did people in the Middle Ages view the natural world? How did they determine if something was true? Directions, read the text and examine the images below, then answer the questions that follow. So here, you may have difficulty seeing it, but here is a model of the solar system, okay? And you see these orbiting circles here, well, they actually look like ellipses, represent planets that we could see at that time. During the Middle Ages in Europe, many of the Roman and Greek texts that contained the knowledge of those civilizations were destroyed because of conflict between kingdoms in Europe. In addition, the use of the Greek and Latin languages diminished. Most people could not read, and there were few books because they took a long time to copy and were very expensive. The centers of learning were universities run by the Catholic Church, so most scholarly pursuits involved analyzing the Bible and other religious texts. When scholars explored science, they did so to prove that the Church's ideas were correct. For example, the the Church taught that the Earth was at the center of the universe. So those who examined the stars looked for evidence that the Sun and all of the other planets revolved around the Earth, rather than following what they observed to a different conclusion. So they observed something in the sky that didn't match up with the Earth being at the center of the universe, or even the solar system, and they tried to scramble to find ways to make that work so that they didn't get in trouble. Outside of the church, folklore and superstition guided an understanding of the world for most people. Medicine, for example, was based on the theory of humors. According to this theory, there were 4 humors, or important fluids, in the body: black bile, yellow bile, phlegm, and blood. Medieval doctors believed that for a person to stay healthy, they needed to keep balance between all the humors. People believed that the humors were produced by specific organs in the body. Changes in a person's mood were affected by the weather, and that people with different astrological signs were prone to imbalances in different humors. If someone was sick and a doctor believed they had too much blood, they would cut the person and drain some of it out, in a process called bloodletting. Depending on the patient's symptoms, the doctors let blood out of a different section of the body. Question 7. Why did medieval scholars not have access to the Greek and Roman texts? 8. Which organization ran medieval universities, and how did this affect the people in the university studies? Or how did this affect what the people in the university studies? 8. We have a double 8. That's okay. Describe the theory of humors. Does your understanding of the human body support this theory? How did most people in the Middle Ages determine if something was true? Okay, continuing on. How did scholars involved in the scientific revolution view the natural world? How did they determine if something was true? Directions. Read the text and examine the images below, then answer the question that follows. Step 1, state the problem. Step 2, gather information on the problem. Step 3, form a hypothesis or educate a guess. Step 4, experiment to test your hypothesis. Step 5, collect, record, and analyze data. Step 6, draw conclusions. And Step 7, communicate, share data, and answer questions. This is the scientific method, guys. During the scientific revolution, thinkers devoted themselves to understanding how we know what we know and how truth is determined. The scientific method led to a shift in the way people understand the world. What is the scientific method? The ideas of philosophers like Francis Bacon and René Descartes influenced the development of the scientific method. The scientific method is a step-by-step process to ask and answer scientific questions by making observations and doing experiments. Why is it important to communicate and share data? The printing press with a movable type developed by Johann Gutenberg and the inventions that improved on his design allowed for an unprecedented level of cooperation among philosophers, who could now build on each other's ideas over long periods of time. Astronomers such as Copernicus and Galileo began to share and build upon their experiments, passing on what they learned so others could innovate. So the idea here, everybody, is that if you were to come up with some amazing idea, let's bring it down to something like a round wheel instead of a square wheel. You would want to spread that information far and wide so that people could take it and improve upon your design. And then over time, it gets better and better and better. If you think about maybe the first automobile with the hand crank, the Tin Lizzies and stuff, look at a Ferrari now and how much better that is. That's all due to passing information on over time and innovating and making something better. Question 10. According to the excerpt above, what technology allowed scientists to disseminate, share their ideas with others? What was the benefit of sharing these new ideas with other scientists and philosophers? How did scholars during the scientific revolution determine if something were true? What ideas influenced the scientific revolution? Where did they come from? Identify where the ideas that influenced the scientific revolution came from and explain how scholars in the scientific revolution built on those ideas. The quote below is an excerpt of a letter from Isaac Newton, 1643 to 1747, to Richard Hooke, 1635 to 1703. Both men were natural philosophers and contributed to the scientific revolution. If I have seen further, it is by standing on ye shoulders of giants. What do you think Newton meant when he wrote, if I have seen further, it is by standing on ye shoulders of giants? 14. What giants do you stand on the shoulders of? Based on the context of the quote. Now, keep in mind, Isaac Newton was a scientist and a mathematician. So what does he mean by that? Think of perspective. If you're standing on somebody's shoulders, you're up higher, you can see further as well. Where did the ideas that influenced the scientific revolution come from? Directions. After examining the text and images on the next 3 pages, answer the accompanying questions, then fill in the table below with the evidence that supports the claim. The claim is, the scientific revolution was greatly impacted by scientific discoveries outside of Europe before the scientific revolution. Like the artists in the Renaissance, scholars during the scientific revolution owed the foundation of their work to Greek, Roman, and Muslim scholars that came before them. The ideas and techniques that enabled the start of the scientific revolution were passed around the Mediterranean world from one golden age to another. Trade between the Ottoman Empire and Europe and the Byzantine scholars who left Constantinople for Italy after the Ottoman Empire conquered it in 1453 led to the rediscovery of Greek and Roman texts that had been kept in the Middle East during the chaotic European Middle Ages. In addition, the Muslim scholars made great strides in science, and their ideas were shared with Europeans and contributed to the discoveries made during the scientific revolution. Scientists in each of these societies added to original ideas, conducted their own experiments, and passed on what they learned. Through this process of collective learning and the evaluation of ideas through the scientific method, individuals who took part in the scientific revolution made incredible achievements that gave humans a greater understanding of the world around them. So, you're going to be formulating evidence to support the claim of the scientific revolution was greatly impacted by discoveries outside of Europe before the revolution began. So look through here on the left and find evidence that supports that claim. Okay? The Nature of Comets from Albertus Magnus. Read the text and examine the images below, then answer the questions. Albertus Magnus, 1193 to 1280, was a German bishop in the Catholic Church, doctor and philosopher who predated the scientific revolution. As a member of the clergy, he had access to scientific texts that most others in medieval Europe did not. The text below comes from a writing of his in which he discusses the nature of comets. We will give the correct view about comets and confirm it by the authority of many physicists. I say, then, that a comet is nothing else than a coarse earthly vapor or fumes. Coarse because if it were thin, it would quickly evaporate and dissolve. It gradually rises from the bottom of the layer of air to the top, where it touches the curved inner surface of the sphere of fire. There it is thinned out by the heat of the fire and inflamed. Its middle always stays dense, but what is thinned out at the sides often seems long, has a thin flame, and is called the tail. The famous philosophers Avicenna, Ibn Sina, Muslim physician, scientist, and philosopher, and Al-Ghazali, Arab theologian and philosopher, give evidence that this is so. Ptolemy, a Greek astronomer and geographer, and Al-Bumasar, a Persian astronomer and mathematician, also imply this. That means they agree. Reason. 2 supports this opinion, since it is evident that the flame is nothing but kindled fumes, and a comet is a sort of flame. As is apparent to the sight, therefore a comet is kindled fumes. 15. Based on this text, what methods does Magnus use to find the truth about the nature of comets? 16. Which philosophers does Magnus cite to support his arguments, and where were the philosophers from? 17. Albertus Magnus states, we will give the correct view about comets and confirm it by the authority of many physicists. What step in the scientific method does Magnus refer to in this quote? Okay, so you're going to have to look back up to the scientific method page and find the step. There are 7 here. Which step does he refer to? And then don't forget, you can use the information you just learned as evidence to support this claim. Okay, so you're going to be jumping around from pages a little bit. Next, we see some artistic depictions. Galen, 131 to 201 in Rome. Mansur ibn Muhammad ibn Ilyas in Persia, 1384. And Andreas Vesalius, 1514 to 1564, Flanders, Western Europe. Muscles Man, a drawing based on Galen's books about anatomy, but drawn by someone else. Mansur's Anatomy, ink drawing by Mansur ibn Muhammad ibn Ilyas, another human anatomy book, and this is an image from Andrei Vesali's De Humani Corporis Fabrica. These all have to do with anatomy, okay? So we'll read this text for each one of those now. Galen was a Greek physician who learned about anatomy through the dissection of apes and pigs, clinical observation, and thorough examination of patients. Galen was forbidden by Roman law to dissect human corpses, so his knowledge was limited to what he could learn from other animals and outward examinations of the bodies of dead gladiators and hanged criminals. All right. 18. What did Galen base his drawings of the human body on? Next, Islamic doctors studied Greek and Roman texts, like those written by Hippocrates and Galen. They then improved upon those texts based on their own observations. One example is Mansur ibn Muhammad ibn Ilyas, a physician in present-day Iran who wrote his book, Mansur's Anatomy, around 1384. The book included chapters on bones and nerves, muscles, veins, and arteries. A concluding chapter discusses the formation of the fetus. How did Mansur build upon Galen's observations? So how did he build upon the observations you see here? Last, Andreas Vesalius, 1514 to 1564, was a Renaissance physician born in Flanders and Western Europe. He went to medical school where it was required for students to study the medical advances made by Arab doctors. Like Mansur ibn Muhammad ibn Ilyas, in addition to reading other writings, Vesalius decided to do his own dissections of human corpses, something that Galen was not able to do. Through dissections, he created a more accurate and detailed depictions of the human body than had ever been created before. So 20, how did he build upon Mansur's observations? 21, what limited Galen's understanding of the human body? 22, how did Mansur go beyond Galen's findings? And 23, how did Vesalius go beyond Galen and Mansur's findings? Let's get the ultimate ones down. Okay? Down here on page 12, we have Ptolemy's geocentric model of the solar system. We have Nasir al-Din Tusi's planetary model right here in the center. And then we have Nikolai Copernicus and his heliocentric model of the solar system. Heliocentric means that the sun is in the center. Here in the picture, you can see it says Sol in the middle. And these are the names of the planets. Venus, right? He's got a little special circle around Earth, Mars, and then we can move on out. Jupiter, Saturn, etc. Okay? So first, Claudius Ptolemy was an Egyptian astronomer of Greek descent who lived in Alexandria, Egypt, when it was part of the Roman Empire in 1500 CE, or 150 CE. He published a book called Almagest, in which he described what he thought the relationships were between the Earth, Sun, planets, and stars. He believed in what was later called the geocentric theory of the solar system, one in which the Earth was in the center and the Sun and the planets moved around it. Ptolemy's was the leading theory for nearly 1,500 years. So the question is, what was Ptolemy's theory about the solar system? Arab scientists examined and criticized Greek and Roman texts. They especially read and discussed Ptolemy. Ibn al-Haytham, one of the leading Muslim scholars around 1000 CE, even wrote a book entitled Shukuk ala Batalamus, Doubts about Ptolemy. Al-Haytham's criticism of Ptolemy's work led others, like Nasir al-Din al-Tusi, to improve upon it. Tusi's model of the solar system was geocentric, like Ptolemy's, but it included a mechanism called a Tusi couple that better explained the movements of the planets. Did Arab scientists support Ptolemy's ideas about the solar system? The answer is going to be no, but you're going to have to tell us why they didn't support it. Nikolai Copernicus was a Polish astronomer who proposed a heliocentric, sun-centered model of the solar system. Copernicus's theory suggested that Ptolemy was wrong and that the sun, not the Earth, was at the center of the solar system. Copernicus's model also included Tussi's couple, but it is unclear if Copernicus made the same discovery as Tussi independently or if he was exposed to Tussi's work. So 26, how did Copernicus support Ptolemy's ideas about the solar system? What new ideas did they suggest? And what new ideas did he suggest? So they being Ptolemy and the two Muslim scholars here, Ibn al-Haytham and Nasir al-Din al-Tusi, and then he refers to Nikolai Copernicus up here. Okay? Page 14. What discoveries were made during the scientific revolutions? What effects have they had? So you're going to read the story below and answer the questions. Hennig Brand, 1630 to 1692, was an alchemist who lived in Hamburg, Germany. Alchemists were people who practiced alchemy, the belief that by experimentation and magic one can turn one substance into something else. During the Middle Ages in Europe, most alchemists attempted to turn inexpensive metals like iron into gold. Hennig Brand tried to make gold out of a substance that was easy to find and similar in color, human urine. According to historians, Brand gathered around 1,500 gallons of urine, then heated it to evaporate the water and experimented on it further. He never turned the urine into gold, but he did discover a white waxy substance that glowed in the dark. In a time before electricity, this was an incredible discovery. Without knowing it, Brand had become the first person to isolate an element that is not normally found by itself in nature. He named it phosphorus. Today, phosphorus is used in fertilizer to grow crops, to make matches and explosives. Brand was the first man of natural philosophers to discover elements during the scientific revolution. So what was Henning Brand's goal? What contribution did Brand make to science? What effects had Brand's discovery had? And what might this story reveal about scientists during the scientific revolution? This one's going to be very opinion-based, but make sure it's rooted in the texts, okay? What discoveries were made during the scientific revolution and what effects have they had? Continued. Mathematics. Here you see Roman numerals on the left, and then the Hindu-Arabic number system, which might look very familiar to you. So if we'd never discovered this, we might still be using Roman numerals today. Natural philosophers who worked to further their understanding of the world during the Renaissance, in what has become known as the scientific revolution, made important advances in a number of fields. Through experiment and reason, they developed theories that were closer to scientific truth. Though many of those theories now have been disproven, their accomplishments made it possible for later scientists to uncover true workings of the natural world. 33. Actually, let's do this one first. What was the effect of the adoption of the Hindu-Arabic number system in Europe? So down here is where you're going to get the answer to that. Roman numerals originated in ancient Rome and were used throughout Europe to represent numbers until the Renaissance. The Hindu-Arabic numeral system was developed in India around 700 CE and was added to and refined in the Arab world and eventually made its way to Europe, where it was adopted by the scholars who participated in the scientific revolution. The Hindu-Arabic numeral system allows for more complicated and precise calculations than the Roman numerals because of the use of zero and the decimal system. The scientific achievements of the scientific revolution could not have been accurately communicated without the use of this numeral system. All right. We're going to continue on now. Botany and zoology. Okay. So we have this Scala Naturae, and the image above depicts the medieval Scala Naturae as a staircase, Raymond Lull's ladder of ascent and descent of the mind. Over here on the right, you have the Systema Naturae, which has the domain, kingdom, phylum, class, order, family, genus, and species that you might remember from living environment class. The modern classification system based on Linnaeus's work. So before we read this, during the Middle Ages, scholars classified living and non-living things using the Scala Naturae, a system that placed things into one of 6 categories: God, angelic beings, humanity, animals, plants, and minerals, and then ranked them within those categories. So this came first. And then utilizing this, in 1735, Carl Linnaeus, a Swedish botanist, a zoologist, and physician, released his book, Systema Naturae. in which he categorized things into three kingdoms: animal, plant, and mineral, then further classified those kingdoms into classes, orders, genuses, and species based on the observation of the characteristics of the animals, plants, and minerals that were categorized. Linnaeus was a devout Christian and is said to have stated God created the lineus organized, but his system differed from the Scala Naturae. Linnaeus categorized humans and animals with apes, and he revised his system as more specimens were sent to him. His system enabled the later scientists to see the relationship between the anatomies of different species and to eventually develop the theory of evolution. Okay. What was the effect of Linnaeus's classification? Answer that right here. Okay. Page 17, chemistry, Aristotle's elements. I love this picture here. Illustration here has earth, fire, you have wind and water there. During the Middle Ages, scholars classified living and non-living things using the Scala Naturae, a system that placed things into one of 6 categories, then ranked them with those categories. It's actually better put up here. Down here, chemistry. During the Middle Ages, alchemists, which were the medieval version of chemists, believed that all things consisted of 6 elements: air, earth, fire, water, sulfur, which gave things the ability to catch on fire, and mercury, which gave things a metallic character. These ideas came from the Greek philosopher Aristotle, 384 BCE to 322 BCE, and the Persian alchemist Jabir ibn Hayyan. Through experimentation, observation, and sometimes mistakes, natural scientists and the scientific revolution discovered that substances could be broken down into elements that were simpler than air, fire, water, and earth. Antoine Laurent de Lavoisier published his Elementary Treatise of Chemistry in 1789, in which he identified elements including modern elements like oxygen, nitrogen, hydrogen, phosphorus, mercury, zinc, and sulfur. The list of known elements has grown since the scientific revolution to include over 100. With the elements identified and isolated, scientists in modern times were able to create new substances like plastic and nuclear energy. Here's a list of the table of elements here. What was the effect of Lavoisier's list of elements? Okay. Continue on to page 18. The contributions and effects of Galileo Galilei, 1564 to 1642. Watch this mini biography of Galileo and read the information below. So make sure you click on this, watch the video. Galileo Galilei was born on February 15th, 1564 in Pisa, Italy. He was a mathematics professor who constructed a telescope and supported a Copernican theory of a sun-centered solar system. Using his telescope, he was able to observe the rotation of planets and confirm Copernican views of the solar system. Galileo was accused twice of heresy by the Church for his beliefs and tried at the Inquisition. At the Inquisition, he was forced to recant, state that he no longer holds an opinion of his belief. His scientific views or risk being tortured, killed, or burned at the stake. The Church was angered that his views challenged the strict biblical interpretation of the creation. God fixed the earth upon its foundation, not to be moved forever. Since Galileo recanted, the Church gave him a lesser sentence for his heresy. He was confined to a house arrest for the last 9 years of his life and not allowed to publish or distribute any of his writings. 36. What contributions did Galileo make to scientific knowledge during the Renaissance? What were Galileo's views about the solar system? 37. Okay. We continue on. The text is the same. The picture here is different, however. 38. How did the Church respond to his views about the solar system? 39. What effects did Galileo's discoveries have after his death? Okay. Put the text here for ease of use, guys, so if you have to look up. Remember, some of your answers are going to come from that video. Next, the contributions and effect of Sir Isaac Newton, 1643 to 1727. Directions. Watch the mini biography of Isaac Newton and read the information below, then answer the accompanying questions. Isaac Newton was born in England on December 25, 1642. He was a mathematician, astronomer, and physicist who was a major figure during the scientific revolution and is regarded as one of the most influential scientists in history. He was a member of Parliament later in his life and made contributions to the field of optics, but is most well known for his accomplishment in the laws of motion, which he published in the book Mathematical Principles of Natural Philosophy, often referred to as Principia in 1687. There's Isaac Newton there. Newton's laws of motion explain the movement of objects on Earth and the existence of gravity. They provided Newton and later scientists with an understanding of the movement of objects and role of forces, that they could use to design complex machines and have fueled innovation to the present time. So his three laws of motion are: an object will remain in a state of inertia unless acted upon by force. The relationship between acceleration and applied force is force equals mass times acceleration. And for every action, there is an equal and opposite reaction. Okay? 40. What contribution did Newton make to scientific knowledge during the Renaissance? What effects did Newton's discoveries have after his death? And then we move into math, which goes right into Isaac Newton once again. So we have contributions and effect of Sir Isaac Newton. We're going to apply the concepts of algebra to the mathematical contributions of Isaac Newton during the scientific revolution. So what were four scientific or mathematical contributions that Newton made during the scientific revolution? We're going to write those answers here. You can scroll up and use the text from the global portion or the video from the global portion to answer those questions, all right? Directions. What are the two values that are most used to calculate gravity? Watch this video here to answer question 2. Gravity. Directions. Fill in the following blanks with words more or less. So here, larger objects exert blank gravitational pull than smaller objects. 4. The further apart objects are, the blank gravitational pull they exert on each other. Okay? Now we come down, before we do 5, we come down here and understand that a Newton is a unit of measure to describe the mass of an object. 1 pound equals 4.45 newtons. Calculate the mass of a 200-pound person in newtons. And you see the example, 200 times 4.45 equals 890 newtons. So a 200-pound person would have a mass of 890 newtons. That's the mass. Calculate your own weight, or you can choose a random weight if you want, to calculate your mass in newtons. So we could do current times 4.45 equals, and we would get the amount of newtons. All right? That's how you do it. Once there, on the moon, would your mass be the same or different as on Earth? Hint here, guys. Is the moon bigger or smaller than the Earth? If it's bigger, it's going to have a certain effect on your mass. If it's smaller, it's going to have a certain effect on your mass. You're going to have to write that there. On the moon, would you weigh the same or different? Note the discussion of the weight of an apple on the moon and why. Don't forget, that's from the video. Why would you weigh more or less on the moon? Gravity, planets, directions. Use the web link to answer the following questions. Here's the planetary fact sheet. This is the web link right here. And we'll read this out loud to you. On Earth, gravity is a constant, does not change. And as we fall to the Earth, we have an acceleration of 9.8 meters per second squared, which is mass over, I think that's mass. No, that's meters, over seconds squared. Okay, that's the way it looks. Each planet has a different gravitational pull. The gravitational pull of a planet depends on its size. So here you see the size of the Sun, then Mercury, then Venus, Earth, Mars, Jupiter, which is by far the biggest. Then you have Saturn, Uranus, and then Neptune. And then way out there, you still have Pluto hanging out. Very small. So, 8. Which planet is the largest and what is its gravitational pull? You're going to find that on the fact sheet. What is the smallest planet? What is its gravitational pull? Would your weight be greater on the larger planet or smaller on the larger planet? What would your weight be? Use the fact sheet. 25. Gravity, the moon. Directions. Use the given equations to calculate weights based on the gravity of the moon. So let's calculate the weight of a 200-pound person on the moon. The moon has a mass of 0.073 times 10 to the 24th kilograms, while the Earth has a mass of 5.97 times 10 to the 24th kilograms. The moon has a gravitational pull of 1.6 m over s squared. Okay, it's meters over second squared, while Earth has a gravitational pull of 9.8 meters over second squared. Look at the mass of the Earth versus the Moon. The first step to calculate the weight of a 200-pound person on the Moon. By the way, if you need to look at the mass again, once again, it's in the planetary fact sheet up here. The first step to calculate the weight of a 200-pound person on the Moon would be to calculate the Earth's gravitational pull as compared to the Moon's gravitational pull. To do this, we would divide 9.8 by 1.6. So you do that and you get 6.125. We would then divide the weight, 200 pounds, by our gravitational factor calculated above, which is 200 over 6.125, which equals 32.7. 11. Calculate what your weight or randomly chosen weight would be on the Moon. So you're going to use these to help you calculate what your weight would be on the Moon. Now, let's calculate your weight on the smallest and largest planets. So we're going to have Earth gravity over that planet's gravity equals the gravitational factor, and then Earth weight over the gravitational factor equals the weight on the planet. Okay? Finding this information on the fact sheet once again. 12. Would your weight be greater on the largest planet, Jupiter, and on the smallest planet, Mercury? Explain your answer here. The laws of motion. Watch the following video on the laws of motion and answer the following questions. Here's the link. What is branch of science deals with how and why things move? So which branch of science, based on the video, deals with how and why things move? 14. Who came up with the laws of motion? How many laws of motion are there? 15. Fill in the blanks. The first law of motion is called, type your answer here. It states that an object will remain at blank or in uniform, constant, or same blank in a blank line unless acted upon by a blank, unbalanced blank. What are 3 examples of external force? Remember, you're getting your answers from this laws of motion video. Fill in the blanks here. The second law of motion states that acceleration of an object depends on the blank of the object and the amount of blank applied. The equation for this is, remember, product means the answer when multiplying. If an object has a large mass, it needs blank force to accelerate. Begin moving. 18. Fill in the blanks. The third law of motion states that for every blank, there is an equal and opposite blank. In the ball example on the video, the action is blank, and the reaction is blank. Think of another example of the third law of motion. Describe it and fill in the action and reaction below. That's right here. Okay. Here's a little picture to give you an idea of where you might be able to go with that. Force. Use the given equations to answer the questions below. Using the force equation, force equals mass times acceleration, solve the following. Force is going to equal newtons, be represented by newtons. Mass units can be represented by kilograms, and acceleration, meters per second squared. All right, so it's meters over a second squared. How much force is needed to accelerate a 66 kilogram skier at 2 times the meters per second squared? Hint, force equals 66 kilograms times 2 times meter over second squared, or force equals 66 times. That's another way it could be represented. So you're going to do your equation out here. Use your calculators, guys. It will help you a lot. What is the force on a 1,000 kilogram elevator that is falling freely at 9.8 meters per second squared? A 50 kilogram skater pushed by a friend accelerates at 5 times meter per second squared. How much force did the friend apply? All right. A bowling ball rolled with a force of 15 newtons accelerates at the rate of 3 times meters per second squared, I should say. So 3 meters per second squared. And a second ball rolled with the same force accelerates at 4 meters per second squared. What are the masses of the 2 balls? All right. So we have to find that out. Here's a little visual example of mass, force, acceleration. Accelerating forward, accelerating forward. The forces applied to the carts is the same. The acceleration of the empty cart is greater than the acceleration of the loaded cart, so the loaded ones. Acceleration increase when a larger force is exerted. So if the cart's lighter, you don't need as much force. If it's heavier, you need more force. That's what that's helping you with. If a 60 kilogram person on a 15 kilogram sled is pushed with a force of 300 newtons, what will the person's acceleration be? So I want to take a second here to go back up to the equation. Force equals mass times acceleration. So what do we have here? what do we have here? We have force equals mass times acceleration, right? So if we're representing force in newtons, that's going to be 300 equals 60 plus 15 times, we're going to use the star symbol here, times x. So that's the way we're going to set up that equation, all right? And really, we can just drop this out because we know that's pretty simple. 75 times x equals 300. So you guys are going to have to then use some dividing to figure out what x is, right? So that's about all the help I feel comfortable giving you without getting in trouble with Mr. Colvin, but that's how you set up your equations. This one just adds a simple extra step of having to combine the kilograms of weight. We get on to page 30 for forensics, okay? Objective is to understand the evolution of science and the dangers of criminal punishment associated with thinking differently than the current authority of the time, the Catholic and Protestant churches. So science, theology, and the Copernican revolution. I'm going to watch the video, and then we're going to read the article and answer the questions using information from both sources. At the beginning of the scientific age, people were not only intellectually shocked, but also spiritually threatened by news that the sun was being asked to exchange places with the earth. In 1612, the devout Anglican poet John Donne wrote these anguished lines in his poem, Anatomy of the World. A new philosophy calls in doubt, all in doubt. The element of fire is quite put out. The sun is lost, and to earth, and no man's wit can well direct him where to look for it. 'Tis all in pieces, all coherence gone. The new philosophy that Donne refers to, since there is no word for science at the time, is the Copernican revolution. In 1610, 2 years before Donne's poem appeared, Galileo Galilei, 1564 to 1642, had published the world's first scientific bestseller, The Starry Messenger. The revolutionary work argued that the heavens are not organized the way astronomers, philosophers, and theologians had taught for ages. As far as Donne was concerned, however, Galileo's ideas threatened not only the entrenched cosmology of Plato, Aristotle, and Ptolemy, but also the religious sensibilities associated for centuries with an earth-centered, geocentric vision of nature. In 1543, Polish astronomer and cleric Nikolai Copernicus had already proposed that the movement in the skies could be predicted more accurately than if one supposes that the Earth and other planets revolve around the sun. However, prior to Galileo's release of the Starry Messenger, Copernicus's new model of the heavens seemed little more than an abstract mathematical scheme for making astronomical predictions. Those who read Copernicus's work often took it simply as an experiment, in thought rather than realistic representation of heavens and earth. For Galileo, on the other hand, the Copernican system was not a mental exercise, but an approximation of the way the heavens really do hang together. In his later and more controversial work, The Dialogue of the Two Chief World Systems, Galileo could scarcely conceal his growing conviction that the Copernican universe must now replace the Ptolemaic one. That means the one where the sun is at the center. So he wants to replace the old one where the earth is at the center with the correct one. His increasingly bold teachings and writings eventually led in 1633 to the Catholic Church's notorious condemnation of Galileo's new science and to his being put under house arrest until his death in 1642. The Church now regrets its mistake and insists that there can be no genuine conflict between science and faith. However, in the 17th century, Donne and many of his contemporaries interpreted the new science as a great threat to spiritual as well as intellectual life. 'Tis all in pieces, all coherence gone. The poet worried, expressing a kind of religious anxiety that still occurs among many people of faith when they hear about the new scientific discoveries. A crossroads for science and theology. Why is there such a fierce resistance to science by so many religious believers? It is partly because faith, theology, and spirituality have always been closely tied to a particular age's picture of the natural world. In biblical times, for example, the religious drama of salvation assumed a three-level picture of the cosmos: the heavens fixed firmly above, the earth beneath, and then lower still, the underworld, Sheol, the dwelling place of the dead. In the 17th century, most religious believers took the biblical portrait of the nature literally. Certain passages in the Bible insinuated that the sun moves and the earth stands still. Thus, the Bible seemed to support the Ptolemaic picture of the universe. while Copernican astronomy seemed to contradict God's word. Galileo's opinion, however, was that the Bible should not be read as a source of scientific information, a position that the Catholic Church now officially accepts. The Bible has nothing to contribute to any knowledge that human beings can gather on their own, that is, with their own natural powers of observation and mathematical reasoning. Galileo continued to believe that the Bible was inspired literature, but he cautioned that people miss the religious meaning of Scripture whenever they treat it as a source of scientific truths. In his letter to the Grand Duchess Christina, Galileo claimed the support of the renowned early Christian writer Augustine of Hippo, 354 to 430 CE. Augustine had pointed out that the Christian instruction should not insist that converts to Christianity take the cosmology of the Bible literally. To do so would only prevent those who can accept the literal cosmology from taking religious meaning seriously in the Scriptures. Some historians and scientists have assumed wrongly that Galileo's clash with his church means that he saw a conflict between science and faith. However, he never thought of his observations and ideas as contrary to the basic teachings of faith. For him, science has little or nothing to do with theology. Nonetheless, the case of Galileo and the entire Copernican revolution, as Donne's poem indicates, did have implications for human spirituality. Spirituality is the quest for a vision of reality that will give people courage, hope, and some degree of happiness in the midst of life's inevitable tribulations. For centuries, Ptolemaic astronomy had provided a framework for spiritual inspiration. For most people, the skies held visible hints of a better world. The perfectly circular movement of heavenly bodies and the faultless spherical geometry of sun and moon, for example, offered at least a hint of the infinite beauty that seemed to lie beyond our shadowy and perishable world. The new science, however, seemed to call all of this in doubt, as Donne puts it. With the more precise astronomical measurements of Copernicus, Tycho Brahe, Johann Kepler, and Galileo, the heavens were undergoing a series of demotions that dimmed their luster. Consequently, the Copernican revolution produced a massive upheaval, not only in science, but also in spiritual life. So, astronomy is a branch of science. Astrology is considered a pseudoscience, which means it's not science at all. Ancient astronomy, philosophy, and theology had all assumed that the superlunary world, the world beyond the orbit of the moon, is special. Above the moon's orbit, the heavens seemed immune to change, novelty, and collapse. Their immutability pointed both minds and hearts towards a better and more permanent world than which existed on Earth. Aristotle had even portrayed the heavens as quintessential kind of reality, far surpassing in value the four mundane elements of earth, air, fire, and water that make up the sublunary world down here. In contrast to imperfect earthly things that change and eventually perish, the heavens seem to mirror the changeless eternity of God. Modern astronomy, however, gradually robbed the heavens of their transparency to God. At least for many thoughtful people like Donne. Tycho Brahe, for example, demonstrated to his shocked contemporaries that comets and supernovae, both implying change and novelty, existed beyond, rather than beneath, the moon's orbit. Thus, the superlunary heavenly vault showed itself to be imperfect after all, and could no longer adequately represent the unchanging perfection of God. Johannes Kepler, moreover, calculated that planets move in ugly elliptical patterns rather than perfectly circular orbits. Careful new observations increasingly demonstrated the heavens, like things on Earth, are ordinary after all. How does all this affect forensics and criminology? Crime was handled by the church in these times, rendering extreme and harsh punishment. As philosophy changed, so did the belief that free will caused crime and not the influence of the devil. As time progressed, so did the fairness of prosecutions. So what Miss Cindy's saying here at the end is that by becoming enlightened to the fact that these scientific things did take place independently of religion, we were able to look at crime and punishment in a way that was a little bit more enlightened as well. Science and philosophy's effect on criminology. Answer the following questions based on the video and article above, and use the line numbers to cite your answers. What happened to Galileo when he tried to publish articles about the sun and the earth? What was the name of Galileo's book? Why was Galileo punished and Copernicus wasn't? Why was John Donne so upset? Remember the poem? What was his quote? What was the church's viewpoint of the earth and heavens and the reason for rejecting Galileo's scientific writings? 6. Why do you think the scientific and medical discoveries took so long to become popular? Hint, how many people could read and who was educated? 7, how did these new ideas begin to change the way crimes were handled? 7 here. 8, using the context of the reading and the internet, define the following words. So you're going to define these words, okay? Let's see here. Do we have a missing form? We do have a missing field, don't we? We'll fix this one before it gets published for you guys, all right? Okay. English. Understand the genre of tragedy, the form of Shakespearean sonnet, and how writing strategy affects the development of a central idea within the context of Romeo and Juliet by William Shakespeare. You are going to complete the reading of William Shakespeare's Romeo and Juliet. That's page 45 through 94. Remember, I know that the modern translation is on the right-hand side, and these pages are not like reading 45 pages in a novel. So you are very capable of doing this in under the period of time, 2 weeks. But you shouldn't leave it to the last minute because that's when it becomes overwhelming. So, directions, you're going to answer the following questions based on the video and article above. Define the terms genre and tragedy, and then explain how genre and tragedy has begun to develop. Okay, so you're going to write your answers here and here. Based on the text, oh, and this is where your explanation goes, by the way, because you must explain how this is becoming a tragedy, this story, all right? How does Juliet react when she hears of Romeo's death? 3, explain how Romeo's banishment is a fate worse than death for the star-crossed lovers. Why would Romeo rather die than be banished from Juliet? Lazy sonnet activity. After reading and watching the video, write a lazy sonnet describing a scene from Act 2. Here's the video here and here. And this is a Shakespearean sonnet which contains the rhyme scheme of A, B, A, B, D, C, D, C, E, F, E, F, and G, G. So, first, you're going to mark the rhyme scheme of the sonnet and see the result of if it matches Shakespeare's. So you have time. Over here on the right, that's the first letter of the alphabet because it's the first rhyming noise. Rhyming sound, I should say. So time goes there. Whoa. Not okay. So we need to have A here. And then so on, you would put B in the next one because that's the next rhyming sound. I don't want to give too much away, so I'm not going to. I guess if you do tab, it fills them all in. That's interesting. Let's see if we can't fix that as well. Make sure you guys don't have any trouble here. So if I did A and then went down, and I changed it to B and went down, it changes them all. Okay, so I'll fix that as well. But as you're filling it in, A, then the next sound is the next letter in the alphabet, so B. And you can use this guide up here, which is kind of a cheat for this activity. But it won't help you too much in the next part, which is creating your own lazy sonnet using the ABAB rhyme scheme. So you're going to create a sonnet using single words per line, so you don't have to write a whole line of rhyme. And how you do that is, let's say, you would start with sunny, right? These are different rhymes, sunny and day. Now you have to rhyme because you have A, B down. Now we need to match A, because that's the third line, with sunny to make it rhyme again. So what rhymes with sunny? Money. How about day? And the difference between what I'm doing and what you're going to have to do is that your rhyme scheme is also going to have to make sense in the context of the play, Acts 3 and 4. All right? So make a lazy sonnet utilizing this rhyme scheme here. And then we're going to get down to the next part, which has to do with pentameter. Is the amount of metric feet within a line of a Shakespearean sonnet and how the words are stressed. Actually, it doesn't have to be a Shakespearean sonnet. Pentameter can go to any type of poetic verse. So penta means 5. If you remember, a pentagon has 5 sides. 1, 2, 3, 4, 5. And so does the pentagram here. 5-pointed star, right? So the line will have 5 metric feet. Pentameter can apply to a written line. So these are the metric feet in sonnet number 12. We have 1, 2, 3, 4, 5 metric feet. I separated them for you. Each metric is established as an iamb, meaning it has one unstressed syllable followed by one stressed syllable. So iambic pentameter has when I do count, the clock that tells the time. Unstressed followed by stressed, unstressed followed by stressed, unstressed followed by stressed. There are 5 of these metric feet, making this line iambic pentameter. That gives you an idea of how brilliant Shakespeare was, because he wrote all of his stuff with these very strict poetic rules. So what you're going to do now is you are going to mark within this line of verse, which is from the same poem, where the metric feet begin and end, and where the unstressed and stressed syllables are by using U and S, and by using the backslash to separate them, okay? When you're done with that, we're going to undertake a text analysis response. You're going to read the passage and identify one of the highlighted writing strategies, the central idea, and then construct a 2 to 3 paragraph response wherein you identify the author's development of the central idea using the writing strategy. You're going to use this portion of the play where Mercutio says, "So if there were 2 men such as you, it wouldn't take long for there to be none, because each of you would kill the other. Why? You would fight with a man if he had 1 more or 1 less hair in his beard than you have in yours. You'll fight a man who's cracking nuts simply because your own eyes are the color of hazelnuts. Only someone like you would look for a fight like that, or that kind of fight. Your head is full of fights as an egg is full of food, but your head has gotten scrambled like an egg from all your fighting. You once fought with a man who coughed in the street because he woke up your dog that was sleeping in the sun. And can you deny that you had a falling out with a traitor because he was wearing a new jacket before Easter? And with another for trying his new shoes with old laces, and yet you're trying to tell me how to avoid fighting?" So Mercutio is telling Tybalt a thing or two right here about how to avoid fighting, reading him the Riot Act. You have to tell me what the central idea of that passage is, and then you have to select between these options which one you're going to use. All right, when you click it, it won't check all of them. It's another quirk I have to fix in this. And then you're going to define the writing strategy you chose. So if you chose metaphor, write it down. If you chose characterization, write it down. If you chose conflict, write it down. I got to tell you, conflict is by far the best choice. Characterization will be second best, metaphor third, and simile fourth. But if you want to try the harder ones, you're more than welcome to. Always go for conflict and characterization first if you struggle, though. Your text analysis response, the directions you must write this response using the passage above from Act 3 as your guide. You have to closely read the text provided and write a well-developed text-based response of 2 to 3 paragraphs. In your response, identify a central idea in the text and analyze how the author's use of one writing strategy, one of these, develops the central idea, okay? I'm going to stop reading these portions of the directions because you know about them now. But important links, there is a rubric and notes organizer in Schoology linked directly here. There's a formatting organizer that tells you exactly how to write this response, sentence by sentence, here if you need those, okay? You're required to identify the central idea, analyze how the author uses the writing strategy you chose to develop that central idea. You must use strong and thorough evidence from the source text, which is up here. I will accept no less than 2 examples, all right? And really you should be doing 3 or 4. So you have to tell me, and the line numbers are right there. So line 20, line 21, line 22. Tell me where you found your evidence within your written response. And my organizer I've linked here shows you how to do that. You must maintain a formal style of writing. No I, me, my's, no more of that. And do not use text abbreviations. If you write cause, you better mean the word cause and not an abbreviated form of because, or you're going to lose credit. Don't type the letter U when you really mean to type Y-O-U, U, things like that. And you're going to follow the conventions of standard written English. If you're not capitalizing words at the beginning of sentences, adding periods, using commas where you need to, and things like that, you are not going to get a good grade on the written response, okay? So make sure you're putting effort into all of that. The central idea, by the way, it tells you here, is the overall main idea of the passage or the universal truth of the passage. It's as if the author is sending you a direct message through this passage. What does he want you to get out of it? And the example I gave is the central idea is that you can get further in life using kindness than being mean. That could be a central idea. This is hypothetical, though. This is not the central idea of the passage. This is just an example of what a central idea can look like. You're going to then write your answer to the text analysis response. down here, okay? You'll be able to utilize all this space, and then if you need to, the rest of the space on page 44. If you have any questions or concerns, please reach out to me, but do not reach out to us until you've utilized all of your resources that we have made for you and linked for you, okay? You have to advocate for yourselves and you have to do some of this stuff on your own. And that means you have to click on these links that bring you directly to Schoology, which I'll show you right now, and show you how to write this type of response. It pops it up right here. There are sentence starters here. There are examples of how to do citations here. It is all here for you. All right? All right, everybody. I hope you enjoyed the video. I hope it was helpful to you. And please use the emails at the beginning of the document if you need any further assistance, okay? 1, 2, 3, 4 emails right there. All right. Thank you very much and have a great week.